Hey guys, welcome to this lesson. So in this lesson, we'll be looking at chapter 2 of this AI agent lesson. So in chapter 1, we look at introduction, what agents are, and we said agents are autonomous systems that can act on their own, think on their own, and perform tasks without human supervision. They are autonomous. They act and they reason, they plan and they carry out operation with minimal human intervention. So, and then we try to differentiate how agents are different from workflow. A workflow is just a system that follow a particular pattern and follow that step to perform a task, while an agent is autonomous. You can use a workflow to automate, but agents are autonomous. That is, they don't kind of follow a particular pattern. They just reason and take strategic step to perform a task, and they also learn, from past experience. So those are what differentiates an agent from workflow. So today we'll be looking at designing agent systems. Please, if you are new to this channel, please kindly subscribe and like. Okay, subscribe and like. Thank you. So designing agent systems. How can we design agent system? In software, everything you are building must have a design pattern. It must follow a particular pattern. It must have what we call architecture. Okay, so that is what the blueprint of the system you are trying to design. So how can we design agent system normally? Okay, so how does agent system really start? Agent does not start like a workflow. A workflow, you have a problem you want to solve and then you build a workflow to solve it. But agent is kind of similar but different in some way. So most agent systems don't start with perfect architecture. Okay, because you just come up with an idea. You cannot build an architecture for an idea that you have not really thought of or clearly. So to build an agent, what you do is you come up with a messy real world problem. You just think of a problem. Okay, and then you think of a foundation model API that you want to use to solve the problem, and then you come up with a rough hypothesis of what could be automated. So you come up with your problem, think of the API you can use to solve your problem, and then you just think of a raw hypothesis, a plan that you can use to automate, the process to solve the problem. So that is the goal we want to look at in this chapter. How can you design an agentic architecture? You have a problem in your mind that you want to solve. You've thought of the API key that you want to use, and then you have your hypothesis. So how can you turn that hypothesis into an architecture that can really solve a problem in real life? So what you do is you start with a narrow valuable slice. Okay, just like, let's say for example, e-commerce. You want to build a customer support for an e-commerce platform that can that can process order or cancel order. So what you need to do is you have a clear input in that system. You have a structured actions to perform. That's the functions. You have a tools and the function of the tools. Then you have concrete output and the fast feedback loop. So what the first agent actually does. So think of the first agent, customer support in an e-commerce platform that can process order, cancel order, and do so many things. Think of the first step in your architecture. What should be the first thing? And then think of how to build the agent to solve that first thing. So let's say we want to cancel order. We want to build an agent that will cancel order. So you have to read the customer free form message before you know whether to cancel the order. Then you have to decide whether a tool is needed. Then you have to call the correct backend tool with correct parameters, and then you have to generate the confirmation message to solve the problem. So this demonstrates true agent behavior. That is, the agent will interpret the customer intent, the agent will choose the action to perform, and the agent will then execute tools and respond coherently to the customer. So that is what the workflow will actually look like. So let's look at an example workflow here. Here we have an AI. This is an example of an agentic architecture. So you have an AI agent here, okay, and you have a web hook is connected to the web hook to get information from the web hook, and then you have a switch uh, that is that allow you to switch rules and routes to each of these. So you can get property from a web, you can get post URL, you can delete or return or something, delete URL or return outputs. So this API, Promos API, that's Wiki API, you can get information from Wiki API. You can also get documentation, API documentation, Google Gemini chat model, and then can route to structure output parser. You can pass structure output parser, and then auto fixing, and so on and so forth. So you can see this workflow. So this is an example of agentic architecture, guys. So let's move into um, our work for today. So we have, as I said, this class is a practical class. So we are going to build and debug in real time. Okay. So multi-component agent architecture is what we want to look at here. So in chapter 1, we built a simple reflex agent, which is just a one-way agent that just reacts and reason. It doesn't keep memory too long, and then it just acts on whatever it's asked to do. And then we use hard-coded logic. So in chapter 2, we are going to use system design perspective here, and how do you architect an agent that scales. So architecting an agent that scale, scalability in architecture is the ability to increase when the workload grows and decrease when the workload reduces in a system. So core design decision covered here are decision. These are the decision, and these are why it matters. Model selection. Different query need different quality, speed, cost, and trade-off. Memory architecture, short-term context versus long-term knowledge. Tool orchestration, coordinating multiple tools per query. Remember, we said tools are just Python functions designed to solve a particular problem, and two have their properties. They have a name, they have a description, and they have a function. Okay, that is what they are designed to do. So cost and latency tracking. Production agent must be economically viable. It must be, it must be very fast. It must be responsive. Okay, so the central class agent orchestrator pulls all of this together. So we have an orchestrator. An orchestrator is what pulls or what pass information to different agents, and it allows them to perform tasks either sequentially or randomly. So an orchestrator is what combine all the agents together and make them responsive. Okay. So to build this multi-component architecture, or the first thing we have to do is we use data classes to avoid boilerplates for data hiding object, and enum to represent a fixed category cleanly. So we are going to import our modules here. Import JSON, import time, from typing import list, dates, and any optional. From data class import data class field, from datetime import datetime, from enum import enum. So we are going to run this now. Okay, so that runs. Then step 2. So with step 1, import module. Step 2, model tiers. So not every query needs the most powerful and expensive model. Okay, so we define 3 tiers here. Fast, in for example, in cloud we have IQ, which is just good for normal tasks. We have Sonnet, which is good for everyday tasks and responds very fast. We have Opus, which thinks deep, and and it uses more token than other one. So when you want a fast, an agent that will perform fast without thinking deeply, I think you can just go with IQ. But when you want a more complex and an agent that can perform everyday tasks, can go with Sonnet. But if you can afford the token usage, you can go with Opus. Okay. So those are the design. So fast one, quick, is very quick, cheap, lower quality, good for simple lookup. Balance, moderate cost and quality, most queries like Cloud Sonnet. Premium, very slow because it thinks deeply. Okay, it gets information from multiple sources. It's very expensive, and but it will give you best quality output, and it's good for complex analysis. So this enum also gives us a clean key for cost and latency lookup. So let's define our model type. Enum: fast, fast, balance, balance, and premium, premium. So this is how you define your agent class. If we are building in real life using API, this will be like IQ, Sonnet, and Opus. Okay, so let's run this. Okay, core data model. So we are going to use our data class to define two plan data holding structure. We are going to use a message to turn that a message to a singleton in a conversation, role plus content plus timestamp. Then we have a to, an agent capability with name, description, and parameter, and it is callable. Okay. Then using the data class instead of plain dict, give us type hint, default value, and representation, string for free. So that's why we are using data class instead of a dictionary. So let's define our data class. Our data class message, role, content, timestamp, and metadata. Then data class 2, name, description, parameter, function, and this one is callable. Okay, so execute the data class, return self.function quirks. So this is how you define data class. So let's run this, and then that's run. So that's step 3, or core data models. We are using data class, and our data model is message and to. Step 4, memory management. How do you manage an agentic memory? Okay, remember we have a short-term memory, which is also called the working memory. We have the long-term memory, which is just like episodic memory. It go back to history and retrieve history. That is long-term memory. So agent need memory to maintain contents across conversation. So we are going to implement two types of memory: short-term, last 20 messages. You can call last 20 messages, and it can also give you active conversation. That's why we call it working memory. Then long-term memory can cause the last 100 messages, and it can refer to historical information in the system. So when short-term fill up, the oldest message is demoted to long-term. So that is when we have up to 20 messages in short-term, then and you want to store more, it starts sending older messages into the long-term memory. Okay, and then when long-term memory messages holds up to 100, all the older one will be deleted automatically in long-term. So in production, long-term memory will use effector database for semantic search rather than keywords. So we are going to get to a place where we are going to define a rack system. So long-term memory are normally uses what we call the effector database, which allow an agent to retrieve information from the vector database and then pass it into the working memory as well, and combine it with what we have in working memory to return output. So this is our memory. This is the memory design, and we have class memory manager, def init self, mask short term int 20. That's we are setting short-term memory to 20, and we are setting long-term memory to 100. Self.short-term list message, self.long-term list message, self.max short-term, max short-term, self.max long-term, max long-term, self.semantic store, dic, string any. So this is the blueprint for the short-term and the long-term memory. And then we are going to define a function that will add message to the short-term memory. Okay, so self.short-term.append message. So this will append message, and if length of the message is greater than what we have defined here, 20, it automatically passes the older one to the long-term memory. So that's what this function does here. Then get recent content, that is get what is currently in the memory. Look at our design here. Active information, it can process last 20 messages, it can also process active information. So we are also going to define it to process active information. So get recent content, save int 5 list message, return save the short term. So that is what is currently processing presently, not the last 20. Then save the search memory, this allow it to return. Remember, you store you append the message, that's you store the message, then you also call the active message, and then you search to retrieve. You have to search the memory holding the 20 messages to retrieve it. So simple keyword search across all memory. Result for message in self.short term plus self.long term. If query.lower in message.content.lower, return or result.append message, return result. So this is what this one does. You define your memory blueprint, you store information into the memory, and then you also process the recent memory, and then you set the memory to retrieve information. Let's run this, guys. Okay, so that is run. And then step 5, dynamic model selection. So how do we select our model that will actually solve the problem? We've defined the tool, or we've defined the the memory, the model class, we've defined the core data model, and we've also defined the model tiers, class, model type, enum, and then we've imported necessary modules. So step 5 now, we are going to define dynamic, or we are going to go into dynamic model selection. So model selector is a selector that routes each query to the right model tier based on 3 signals. So it routes based on urgency, based on budget, and based on query complexity. So if the information is very urgent, that is, if it belongs to the class high urgency, it always gets the fastest response. And if you are working on budget, add cap forces, downgrade if needed. So it will use the medium one, the one in the middle. Then if you want query complexity and you have your budget is very high, it will go into the long queries or keyword like analyze, which is the premium model. So this is rule-based selector. In production, you might train a classifier or use an LLM to make this decision. So it is as like I told you earlier when we were defining our model class. If it is LLM like Claude, you are going to define use IQ for the lowest urgency one. For budget, for your budget range, you can use Claude Sonnet, and for query complexity, you use Opus. So this is our model selectors. Def init model class model selector, def init self dot model cost. So it's classify the cost whether fast, balanced, or premium. Self dot model latency, that's how fast you want the model to perform: fast, balanced, and premium. So these are the type, these are the parameters that we have defined for them. Def select model, self query, string urgency, string normal, budget, float, model type. So query length dot query. So this one allowed this function allowed the agent to select, to pass query to the model type based on the urgency of the information. So if the urgency is very high, it's passed it to the fast. If the urgency is less than this parameter 0.002, it passes it to fast. It's still fast. If the budget is less than 0.01, it passes it to balance model. Okay, so balance one model type. And if the query length is greater than 50 or analyze is included, it will pass the query to premium model for processing. So def get model info. So this function will get the model information and then return it. So let's run this. So that has been run. So now that we have defined our model type and get model information, the next thing is to define our orchestrator or agent, the agent that will orchestrate everything together. So this is the competence of chapter 2. It wires together all components: query, model selector, memory manager, tool selection or tool execution, and LLM call to response. So this is what the architecture look like. So this is what our architecture look like, from query to model selector to memory manager to tool selection to tool execution to LLM call, and then you have your response. So each step is logged with timing and cost data, giving you full observability into agent behavior. So I have not, I draw this architecture somewhere, so maybe I'll show you before the end of the class, but this is the blueprint, this is the design pattern for this particular agent we are processing in chapter 2. So notes, simulate LLM call in real system. This is where you call the Cloud API. So here we are just using, hard coded. We are not calling API yet, but here you have to, if you are building for production, this is where you call your API. The simulate this simulation let us learn the architecture without needing API key. Okay, so we don't have to waste money here. We can simulate, and then when we want to build for production, we can now call API key. Okay, so we are going to define our orchestrator class agent orchestrator. Then we define the blueprint: def init self name string agent self dot name self dot to self dot memory self dot model selector self dot execution log. So you can see it's actually follow the design pattern. So it's self dot name, that is the agent name. It knows this orchestrator agent will know the name of all all the agents that are registered under it, but the name of the orchestrator agent itself is agent orchestrator. Self.to, that is the tool we are defining, we are passing into it. Self.memory to call memory. Self.model selector to select a particular model to you from fast, from urgency to fast and to complexity. And the self.execution log, that's tool execution, LLM call and response. So execution log. Then after calling the tool, we register the tool under the agent, under the orchestrator agent. Self.to goes to 2, then we print the 2. Then after that, we define a function to simulate LLM call. Okay, so this is where API key of any model you are using will be called. Time.sleep self.model selector.model latencies, response model type fast, model type balance, model type premium. So it return all the model that you have there, return response. Then select two function. So this function allow the agents to select two to use two for the problem, and then it returns the two. Then process query. After selecting query, it calls a model type, it selects two to solve the problem, and then it start query, it start processing the user query here. So model type self.model selector, so it's choosing the model to use from the three: query, urgency, budget. Based on urgency and budget, select model info self.model selector get info, that's information of the model type selected. Then orchestrator model type dot value estimate cost model.info. So this process the processes the customer's cost and budget, and then passes the information to the right model. You can see the work of the orchestrator coordinate all the activity of the agent. So context, self.memory.get recent context. So the recent context, remember we have the working memory and the long-term memory, and in the working memory we have last 20 messages, and then we have the recent messages. Okay, and then the long-term memory we have about 100 messages stored. So get recent memory, that's this from the short term. And the user message row, user context query self.memory.ask message. So it add the message in the recent memory to the current message that it asks in the active memory. and then select to, self.select to query. So it select it to process the query, and then to selected. To result for to in select to, try result to dot execute query, to result to dot name result, print to dot name, except exception as a, to result to dot name error. So if it does not find any two, it will return error. And then response, so that's the final response. Self dot simulate LLM call model type. So LLM call the model type, uh, pass process the user message plus the context, and then store the information in the memory, add the result into the memory, add message, role assistant, context, response, metadata, model type, value, and then execution time. Time minus start time. So present time minus start time, that's the execution time. Self does execution log dot append dot model type dot value to use execution time and cost model info timestamp. So this execution time allow it to store the time that each model or each message is stored in the memory, so it can know the one to the one that is older and the one that is recent. And then return response. So this will return the response to the user. Okay, and then get statistic. So statistic of the messages we have in the short term and the long term, and the cost statistic, the average processing time, and the most used model. So the model that is being most used, and then it returns the query and the statistic. It returns total query, total cost, average execution time, and most used model. So let's run this function, this class of function. So it is run successfully. So this is how you define orchestration and how you define a function under it to route through the entire architecture, from query to model selection to memory manager to tool selection to tool execution to LLM call and to response. So if we're using if it were production, we are going to call our LLM API here, and then we are going to process whether it is IQ or Sonnet or Opus. So step 7, tool implementation. So 3 simulated tools are defined here. So in production, each will call a real external service, okay, not a hard-coded tool. So we have 3 tools here. We have web search tool, which return passes the process the query based on a search information from the website, and then simulate it. Calculator selector. So we have a calculator selector tools which allow you to calculate, to perform arithmetic operation. And then we have database query tool, so return database result. So we have these 3 tools here: web search, calculator, and database query. So let's run our tools. So our tool is now also run. So return the demo. So we are going to demo this now. We have defined our tool, we have defined orchestrator class, and the function of the orchestrator, and how to walk through the entire architecture to to process the query and return response to the user. So 4 test query with different urgency and budget setting. Watch how the model selection changes. So we have agent orchestrator, name demo agent. So the name of the agent is demo agent. Remember our blueprint, self.name equals to name. So now the name is demo agent. Agent.register to or web search. The parameter is query string function. The function of the web search tool is to is web search. That's to search the web. Agent.register to, the second tool, which is calculator. Description, perform calculation. And the function is calculator, to calculate, calculator 2. And then what the parameter is expression, and it is string. Parameter of the register to or website to is query. Then agent.register to name database query, description, query internal database. Okay, remember we have internal database, short term and the long term. Parameter is query and the function is database query too. So let's run this. So we've run the demo and all these tools are registered in our agent orchestrator. Now the next thing we need to do is test cases. So let's test each of these two whether they will work. What is 25 plus 30? This one will go into calculator, and the parameter, the temperature is 0.01. So which model 2 will it go to? Search for latest AI developments, 0.005. This will be web search. Analyze the complex relationship between ML and quantum computing. So this should go to, or web search as well. Quick database lookup, so this is, complex analysis. So this will go to, the premium model, which we define. It will use analyze. So for query urgency budgets, as we have defined our memory in test case, so print each of these results, and let's see. So you can see query, what is 25 plus 30? It is very urgent and it is normal. The budget is 0111. So the orchestrator model fast. So the fast model will process this, and the cost is $0.011. The memory is 0, context message retrieved, 2 selections selected. To select the calculator too. You can see the orchestrator is working. Result model fast, time. It returns time and cost. You can see the orchestrator is actually functioning and it's returning. Now let's see the search for latest AI development. It passes to, urgency, very high, budget $0.005. So orchestrator determine the type of model fast, estimated cost 0.001. So it chooses memory, 2 context message retrieved from memory, 2 selected, it selects web search 2, okay. 2 web search result for search for latest AI development simulated, and result model fast times 0.001. So the fast model will process this, and the 2 selected is web search. Analyze the complex relationship between ML and quantum computing. Urgency is very low, budget is 0.03. Orchestrator, we use premium model here, and the cost is 0.02. So memory, 3 context message will be retrieved from the memory. Selected database query, so it's passing this to database query. To database query execute for quick message lookup simulated, and the model fast time 0.001. So output truncated. So I think you understand what the orchestrator messages does here. Okay, just let's use this 3 as an example. Okay, so this is how it works, guys. And then print execution statistics. So what's our execution statistic? This is what we have. Execution statistic: total query 4, total cost 0.023, average cost time, average execution time 0.27 seconds. Most used model, we use fast. That's the we do not use urgency. Okay, yes, we use fast memory. So this is how orchestrator agent works, and this is how an agentic design pattern is. This is how you design architecture of an agent from query to response given. So in chapter 2, we've looked at model tier, model type enum, 2-tier. We implemented 2-tier memory using memory manager. We use dynamic model selection, model does select model, and then we build full orchestration pipeline, which is agent orchestrator, the process query, and then we try to process and log the cost and performance tracking, which is monitoring. So this is a scalable agent that we just built. We implement log and monitoring system, and then our metrics, we determine our metric based on our statistic, which is execution log plus get statistic. So So what still simplifies? Simulate LLM call. Remember, we just use hard-coded. We did not use API. Search memory, use keyword. We did not use a vector database yet. So to selection, we built hard-coded two, web search calculator, and the other one. Alright guys, so this is the entire workflow combined together. We used a notebook to explain, but this is the entire workflow. So design agent system, multi-agent, multi-component agent orchestrator to combine components together. So we have demonstrated model selection and swapping, to integration and pattern, memory management, and orchestration agent. So this is all the code combined together step by step. We imported our modules, then we defined model type class, and then we defined our data class, which is message and to, and then we defined our memory manager, short and long-term memory, and then we defined our model selector from fast, balance, and premium, and then we defined the select model function based on budget and urgency, and then get model info function. Then we define our orchestrator class. Okay, we initialize the class, we register to in the class, and then we define a function to process query, to select model, to get memory contents, uh, create user message, determine the tool to use to process the message, execute tools if needed, and generate response, which is the output, which is the entire design, and then store response in the memory, and then log execution, and then generate statistics, simple keyword matching. And then this is all we have, and this is our tool definition, and this is our database query tool. This is demonstration, solving real problem, create orchestrator, register through, test queries, and then show statistic. And then if we run everything, we'll see the exact same thing that we have seen in our notebook. So you can see it works. If this is real life now, it will process in real time. So this is how it works, guys. Connecting to Claude. So to connect to Claude, we are going to replace simulate LLM call with real Claude API call. Then add Anthropic API key. This format is what you use, and it normally start with skant to your .m file. So you will have copied the key from Anthropic Claude API, model tier, Claude model, fast, Claude IQ, balance or premium, Claude Sonnet. So we are going to use Sonnet for both balance and premium. And then you have to import the following: import sys, path from pathlib, import path, sys.path.insert 0, path.resolve parent. From config, import get Anthropic client, print Claude. And then we'll define the Claude models. So these are model fast, IQ, balance, Sonnet, premium, Sonnet. So we will not be using Opus because of the cost. It's very expensive. So class, we now define our agent orchestrator with Claude. So agent orchestrator, so extend orchestrator function above. So simulate LLM call, walk through the LLM and call the right one, and it return the response. And then we have agent orchestrator with Claude, agent live dot register to, it register of the two we have defined, parameter expression string function calculator to result, agent live dot process, live process, and so on. So we are not going to process this now, guys, because we have not put our Claude API. So this is where you are going to paste your Claude API key. So when I subscribe, I'm going to show you how to paste API key and how to get it and paste it here. If you are using OpenAI API, I'm going to use this format, paste it here. If you are using Travely API key, you're going to paste it here. So this is how it works, guys. So please remember to subscribe and follow along, and tell someone to also tell someone about this channel, because we are going to learn a lot. All right, bye, see you in the next lesson.